Hi, hello, namaskar. So today we shall take integrated rate equation for first order reaction. Okay, and before that, welcome to chemistry here. So first order reaction means what? If the rate of reaction is directly proportional to the first power of concentration of reactant, then the reaction is called a first order reaction. Okay, so for that reaction we will take integrated rate equation, and how we get this equation, that is what we are going to discuss. Okay, so suppose we are having a reaction where reactant R is getting into product, and this reaction is following first order kinetics. Okay, so like in the previous zero order reaction we have done, if the time t is equal to 0, then the concentration of reactant is R naught and concentration of product will be of course 0, and at time t the concentration will become R. Okay, and this will become what? R naught minus R is equal to what? Is equal to X. So this is our first order reaction. For that we have to consider integrated rate equation for this reaction. So let us first take the differential rate equation, and that will be equal to minus dr upon dt is equal to k1. K1 is what? Rate constant for first order reaction, and k1 K1 what? R. K1 R, because R is our concentration at time t. Am I right? So this is what called what? The differential rate equation. What may we call it? The differential rate equation for first order reaction. We may rearrange it like dr, okay, upon R is equal to minus k1 dt. Okay, dr upon R is equal to minus k1 dt. So this may be also we can say the differential rate equation for first order reaction. Okay, now integrating this equation. Okay, so if we integrate this equation, then what will happen? This will happen, of course. So integrating this equation, what we get is integration of dr upon R is equal to minus k1 integration of dt. Means integration is done for the variable values. Okay, for constant there is no integration. So integration of dr upon R is equal to what? Log natural, that is ln. Ln means log natural R. Okay, log natural R will be equal to minus k1 t and plus I, where I is what? The integration constant, and the value of I can be calculated on the basis of conditions. So which are those conditions? If t is equal to 0, then R will be equal to R naught. If t is equal to 0, then what? R is equal to R naught, and hence I will be equal to ln, means log natural R naught. Suppose this is equation number 1 and this is equation number 2. So putting value of I from equation 2 to equation 1, what we will get then? Log natural R is equal to minus k1 t plus log natural R naught. Okay, so this is again like a straight line equation. Okay. Or what we can write, this is suppose equation number 3. We will take it later. Okay, so ln R we can rearrange this. Okay, if we take this ln r into this side and this k1t, so minus k1t is equal to what? Log natural r naught minus log natural r. Okay, and sorry, this minus will not be there by we have taken this, so this minus will become plus, of course. Okay, so k1 will be equal to what? 1 by t log natural. See, this is log natural r minus log natural r, log natural r naught minus log natural r. This is like log natural a minus log natural b, and that is equal to log natural a upon b, means r naught upon r. You can write this like this. Okay, so or what we can say, if we convert this log natural, okay, we convert this log natural into log base 10, log base 10, then what we will get is, we will get, means if log natural is converted into log base 10, then the value is multiplied with 2.303. Remember this, 2.303. So then what will happen is, k1 will be equal to 2.303 upon t, okay, log base 10 now. Now this is log base 10, this is log natural, this is the difference. Log base 10 will be 2.303 multiplied with this value. So log r naught upon r. Okay, so this is the equation using which we can calculate the value of rate constant for a first order reaction, the integrated rate equation. Am I right? So this is how we can calculate. Now see, if we plot a graph, say this equation, if we plot a graph, that is why I said we will take this later. So if we plot a graph between log natural r and time t, okay, then what we will get? We will get a graph like this with a negative slope, okay, minus k1 t. Okay, so this is what y is equal to mx plus c. Am I right? So this is what? The intercept. This intercept is what? Log natural r naught. Okay, because the concentration of reactant will decrease with time. That is why the graph will come, or the graph will come as a negative slope. Okay, and the slope of that graph will be equal to minus a k1. Slope will be equal to that m constant, that will be equal to slope. So since it is negative slope, and that is why slope is minus a k1. If we plot a graph between log base 10 r naught upon r, okay, means r naught upon r. R naught means initial concentration, r is concentration at time t. So with time the concentration of r will decrease, hence the value of log r naught upon r will increase, and that is why we will get a positive slope. Am I right? And log r naught upon r upon your time. If we plot a graph between these two, then we will get the straight line graph like this, and from this equation, see this equation, okay, from this equation if we plot a graph, then what we will get? Slope will be equal to k1 2.303. Okay, we can rearrange this like k1 t upon 2.303, okay, like k1 t upon 2.303 is equal to what? Log r naught upon r. Alright. So from here what we can see, if we will plot the graph, means this is y axis, okay, and mx, there is no intercept, okay, there is no plus c, so no intercept is there, graph is starting from 0 itself. Okay, so this is clear from here. Okay, so then the slope will be equal to what? Slope will be equal to k1 upon 2.303. That is what? Slope will be equal to k1 upon 2.303. Okay, so this is how we can extrapolate the graph and we can calculate the value of K1. K1 means the rate constant for first order reaction. So this is how we derive the integrated rate equation for first order reaction. Now if say we are taking 2 time interval, and at 2 time interval we are considering the concentration of reactant as R1 and R2. What? R1 and R2. Say here, like the concentration here, this is R1 at time T1 and R2 at time T2. Then we will have 2 equations like ln R1, okay, ln R1, ln log natural R1 will be equal to what? See, I am taking this here, and this is ln R naught K1 T1, okay, will be equal to minus K1 T1 and plus ln R naught. Am I right? So this is how we can write at a time T1 the concentration of reactant is R1. So this is how that equation will become. Am I right? Now what we have done? We have taken this here and we have taken this here. That is what we have done here. So another equation will be like log natural R2 will be equal to minus K1 T2 plus log natural R0. Am I right? Say this is equation number say 4, or this is equation number 5. If we will subtract the equation number 2 from 1, because R1 is greater than R2. Am I right? So what we will get? We will get like K1 we may take common, and this will become log natural R1 upon R2. Am I right? Because ln R1 minus ln R2 will be equal to minus K1 T1 will be equal to minus K1 T1 plus log natural R0, okay, and then minus this one. So minus plus, okay, so plus K1 T2, and this will become minus ln R0. So this is plus ln R0, this is minus ln R0. They will cancel each other. Am I right? Like this. And what we will have? We will have K1 as common. K1 we can take here common. So what we will get? T2 minus T1. What we will get? T2 minus T1. So what we will get here is log natural R1 upon R2 is equal to K1 delta T, T2 minus T1, and that is delta T, time interval. Or what we can write, we can convert this into what? Like K1 will be equal to 1 by delta T log natural R1 upon R2, or what we can write? Or we can write K1 is equal to what? 2.303 upon delta T log R1 upon R2, where R1 is the concentration of a reactant at a time T1, and R2 is what? The concentration of reactant at time T2. Is it clear? So at different time interval we can use this equation. If we have been given 2 concentration of reactants at 2 different time interval, that is T2 minus T1. So we can use this equation and calculate the value of rate constant K1. Is it clear? So this is how we can derive the integrated rate equation for a first order reaction. Now if we want to derive the half life, okay, half life means the time taken for completion in 50% of that reaction, okay. So that is what is called a half life, and in that case what will be our K1, okay. If the time t is equal to t half, okay, then what r is equal to r naught upon 2. Am I right? So we can put this value into equation number what? Equation number, this is say A. This is equation number A. So putting the value of t and r sorry. So we can put the value now. What we will get then? K1. Okay. K1 will be equal to what? 2.303 upon t half, because instead of t we have t half now, okay, and log r naught upon r naught by 2, okay, because r is equal to what? R naught by 2. So this r will cancel each other and this 2 will go up, and we will have K1 is equal to what? 2.303 upon t half log 2, okay. The value of log 2 is equal to 0.3010, so we can put that value here, and we will have that t half, let me get here, t 1 by 2 is equal to 2.303 into 0.3010 upon K1, and this is equal to t half is equal to 0.693 upon K1. So from this equation we can calculate what? We can calculate half life of a first order reaction. Am I right? So this is quite easy, and this is showing and this is proving that the half life of a first order reaction does not depend upon the initial concentration of a reactant or the concentration of a reactant. Whatever the reactant is, the half life will be same for a particular reaction. If we want to exemplify this first order reaction, then all the artificial and natural radioactive decays, which one? The radioactive disintegration and radioactive reactions are follow first order kinetics, okay. Another example is if we decompose N2O5 dinitrogen pentoxide into N2O4 and oxygen, then that reaction also follow the first order kinetics. And except from that, if we hydrogenate ethene with the hydrogen, then also the reaction follow first order kinetics. So many another examples are there that you must study. So that's all in the integrated rate equation for first order reaction, and some graphs we have discussed, and half life of course, and half life, that is what is very important, and half life is independent of the concentration of reactant for first order reaction, while in case of zero order reaction we have seen that the half life of that reaction is directly proportional to the concentration of reactant, but that is the different case. So that's all for the day, and happy chemistry. Keep watching videos, support the channels. Thank you very much.